Hi everyone, here's the next video in this series. Sorry it took so long to get it posted. I have several examples we're going to go over here since this is a problem type that people typically do not get correct, and we want to make sure that we do get it correct, so we're going to handle several different cases here. So the first one we're going to look at is the function f of x equals 7 over x minus 4. And the question is, what is the domain? So notice that here I didn't write the question, but the topic is domain, so that's what we're going to be interested in all these problems. So the idea here, let me change the color pencil here that I have, is that we want to figure out what values of x make this function undefined. So for fractions, or rational functions, I'll write this above, for rational fractions, or for rational functions rather, we set the denominator equal to 0. And whatever values of x you get, are the values that we're going to have to exclude from the domain, and then everything else in the real line will be part of the domain. So in this example, we're going to take this x minus 4 that I've circled in red, and we're going to do some side work here. And so I'll go back to the other color here, and we're going to look at x minus 4 equal to 0. And so the idea here is that we want to solve for x and see if we get any real values for x. And again, we're adding both 4 to both sides of the equation. And notice that we get x equals to 4. So what are our possible solutions? There's a couple different ways to write this. One is just that all real numbers except 4. Another way to write this, so these are equivalent solutions. So another way to write it is that you have the set of x such that x is not equal to 4. This would be an example of a domain as well. We could even write this in interval notation as negative affinity to 4 union 4 to affinity. These are all acceptable types of solutions for this problem. So that's it. So I'll put my little box here to indicate this problem is done. And so notice that this function only has one place as undefined. If we look at this graph, we'll see in a later section that we actually get a vertical asymptote at x equals 4. And that's kind of a different topic entirely, which we'll talk about at a later time. So let's look at this problem. Again, we want to know where the domain is equal to 0. So again, we're going to take x squared minus 16 and do some side work. So we'll change back our color and do the side work. So we are going to get that x squared minus 16 equals 0. We add 16 to both sides, and we'll get that x squared is equal to 16. And then using the square root property, we get that x is equal to plus or minus 4. And so our solutions, there's again several different ways to do this. This is all real numbers except x equals plus or minus 4. That would be one way to write it. We can write the set of x such that x is not equal to plus or minus 4. Or we can also write it in interval notation as negative affinity to negative 4, union negative 4 to 4, union 4 to affinity. And if you're kind of having trouble with the interval notation, think about it this way. You can draw a number line And at -4, you're going to have an open circle, and at 4, you're going to have an open circle. And think about the open circles corresponding to the unions, and then the -4 itself just goes on each side. In this part, and then the 4 goes on each side on this part. So that's one way to keep straight the interval notation. And the same thing actually works on the previous problem as well, but I'm not going to backtrack to that problem and redo that. I'll leave that for you if you want to do it on your own. So this problem is now done. So let's get rid of all this extra junk so it looks nice and neat, so you have something good to copy from. Alright, so we got 2 more examples here, so let's move up and move over. The next example here is that we have 3 over x squared plus 1. And so here again, actually I should have kept my color. We're going to take this value and do some side work. And so we're going to look at x squared plus 1 equal to 0. And subtracting 1 from both sides, we get the x squared equals -1. And notice that this has no real solution. So in these problems, these functions, we're only looking for real values. So if we get something that does not give us a real value, then there's no numbers to throw out. And in fact, our domain then is, for this function, all real numbers. So if you say it in words, you can write it like that. You can also use interval notation, which is negative affinity to affinity, or you can use this r with the extra bar that we saw in a previous video. Now finally, let's look at this example here. So let's draw a line here, make sure we keep those two separate. And for this problem, we're going to have to factor the denominator. And we're going to have x minus 2 all over x plus 1 and x minus 2. And we have to be very, very careful here. You must find a domain before canceling. So let's do that. So this is going to be, let's again take our red pen. This is the factorization we're going to work at, and so we're going to do our side work. And this is going to be x plus 1 times x minus 2 equal to 0. So the zero product property applies, and we get that x plus 1 equals 0, or x minus 2 equals 0. In the first equation, we can subtract 1 from both sides. These cancel, and we get x equals -1. Or on the other equation, we can add 2 to both sides, and we get that x equals 2. So our domain here for f of x, let's write it, is that, so again, we can just write it in words, all real numbers. Oops, that's not how you spell numbers. Except x equals -1 or x equals 2. In terms of set builder notation, we'll use this ugly bracket, the set of x, such that x is not equal to -1 or x is not equal to -2, or we can use interval notation again, negative affinity to -1, union -1 to 2, union to affinity. So any one of these answers, these formats for the answers is acceptable. So let's, before we stop this video, let's think about this function and simplify it further. So if we simplify it one more step, we get that this looks like 1 over x plus 1. So let's graph the two functions in our graphing calculator. So I don't have that open yet, so sorry, I need to open up the start menu here and open up the graphing calculator. So let's clear the previous example out. From when we were solving systems here, let's turn the zoom to normal. And let's type in, so this is going to be x minus 2 divided by x squared minus x minus 2. And then let's look at the graph of 1 divided by x plus 1. So first thing we're going to do is we're going to get rid of the equal sign as soon as the calculator catches up to me. And we're just going to graph the first function in blue. So let's see what that looks like. So that's what the graph of x minus 2 all divided by x squared minus x minus 2 looks like. So now let's impose the graph of red on it. So what happens after we make the cancellation? And if we graph it, notice that the red just traced out the blue. So our equal sign is justified that these two functions in some sense are equal. But there is some sort of caveat here. This is only true when x is not equal to 2. Because, notice when we go back to our function here, this function here is defined for x equals 2, and this function here is undefined for x equals 2. So this division only can occur when x is not equal to 2. And let's see what happens when we go to our table. So let's go to window table set. So second table set. Let's start at -5 and go by values of 1. Now, going to the table, notice that at -1, we both get an error in both functions. So remember that y1 is before the cancellation, y2 is after the cancellation. But notice that at x equals 2, y1, our original equation, has an error, while y2, our function we get after the cancellation, does not have an error. So what this happens is that when we cancel x minus 2 over x minus 2, we are actually creating a hole in the graph. So this function, y1, looks like the graph of y2, except at x equals 2, where we made the cancellation, we're just going to have a hole in the graph, which is represented by the error that you see on the table. So there's no real good way to show this on the graphing calculator, so this is something you would just have to draw by hand and put a little circle in on the y-coordinate above x equals 2. So keep that in mind, that when you cancel off a factor like this, the resulting function is going to be graphed like the function after the cancellation, but you're going to have a hole at that factor that you canceled at. So, right, I just want to make that point out because that's a subtle point that will come up again in Calc 1. And it's good to know anyways because it's the behavior of rational graphs, which is something we should know anyway. So thank you for listening to this little extended part of this problem, and we'll move on to domains of radicals.